Today I'd like to talk about Richardson's extrapolation. This is a technique by which you combine several not very accurate approximations to a quantity to obtain a more accurate approximation. So we'll state our official premise here. We want to calculate some quantity q. It might be, for example, the integral from a to b of f of x dx. But all we know how to do is to do approximations which are based on some spacing h, a of h. So for example, a of h might be the trapezoid rule using h as the delta x as the spacing. Furthermore, we're going to assume that everything is nice in the following sense. If I look at my approximation, it differs from the true value by a power series involving the spacing h, which, as I said, secretly is delta x. What we're going to do is we're going to pick some initial value for this h, calculate the approximation based on that spacing, then calculate the approximation based on h over 2, h over 4, and h over 8, and then somehow in some clever way combine these approximations to get better ones. We're going to make a table. In many ways, it's very similar to the table we used in polynomial interpolation, except I don't have any x values. Column 0 of my table is going to be the approximation based on h over 2 to the 0, which would be based on h, the approximation based on h over 2 to the 1, and the approximation based on h over 2 to the second power. If I had more horizontal rows in my table, I would have a based on h over 2 cubed, h over 2 to the 4th, and so on and so forth. We're going to build up a table. I'll have numbers t11, t21, and t22. I'm going to try to mimic the interpolation table as much as possible, but my goal is to get more accurate approximations. In fact, I'm going to mimic the behavior of the Newton table so much, even the dependencies are going to be the same. To get this number, I'm going to somehow combine the number immediately to the left and the number above. I will do the same for t21. Once I know those two numbers, which in some sense should be better approximations to the actual quantity that I'm interested in, somehow we will combine these two numbers and hopefully get an even more accurate approximation, that is. So my row indexes and my column indexes are going to be just as in the Newton table. What follows is a large mass of algebra, so it's better to look at it when you can pause the video, for example. If I think about t00, this is the approximation based on h over 2 to the 0 power. That is just the approximation based on h. And our presumption that everything is nice means that I can write out the series expansion. t00 is the true value plus alpha 1h plus alpha 2h squared, and so on and so forth. t10 is the approximation based on h over 2 to the 1 power. I'm not going to do anything mysterious here. I'm going to take this formula for t00, and every place where I see the letter h, I'm going to write down h over 2 instead. So instead of alpha times h, I would have alpha 1 times h over 2, which I'll write this way. The square of h over 2 is 1/4 h squared. If I cube 1/2, I get 1/8, and so on and so forth. What I want to do is to combine those two formulas in some way so that I get a more accurate representation of the value of Q. If you look at these two formulas, T00 and T10, this doesn't depend on the spacing, and this term and this term differ by a factor of 1/2. And that's what's going to tell me what to do here. I'm going to write this in a rather odd-looking way. I'm going to take T10 and multiply it by 2 to the 1 power. That would then be 2 times this quantity, 2Q, plus 2 times 1/2 times alpha 1 times H. That would be alpha 1 times H. 2 times 1/4 times alpha 2 H squared would be 1/2 alpha 2 H squared. 2 times 1/8 is 1/4, and so on and so forth. The T00 quantity is Q plus alpha 1H plus alpha 2H squared, and so on. And what we're going to do is we're going to subtract these two things. I'm going to calculate 2 to the 1 power times T10 minus T00. So I'll write that down. This is 2Q minus Q, which is Q. Because of the way I've carefully rigged these formulas up, these two terms are the same. So when I subtract, the H to the first power term goes away. If I have 1/2 alpha 2H squared and subtract away alpha 2H squared, I get minus 1/2 alpha 2H squared. And likewise, when I subtract these two terms, I get minus 3/4 alpha 3H cubed, and so on. It may not look like it, but a small miracle has just happened. There's this quantity, which if I already know column 0 of my table, I can easily calculate. That quantity is the true value that I'm looking for, plus an infinite series in terms of the spacing that starts off with an H squared term. We have eliminated the H to the first power term here. 2 to the first power minus 1 is just 1. So I can write my result this way, although it looks rather odd. This quantity is the true value that I'm looking for, minus a power series that starts off with minus 1/2 alpha 2H squared. This combination is what I'm going to call T11, and it's more accurate, generally speaking, than any of the numbers in column 0 were. So far, here's our plan. We calculate column 0 based on various spacings. Then T11 is going to be the quantity that we just listed. And the important thing about T11 is it differs from the true value by a power series that starts off with H squared. We've gotten our results so far by looking at the first two numbers in column 0, but I can also think about looking at the last two numbers. I want to compare T10 with T20. We've already figured out what T10 is. If you return to the original expression for the approximations in terms of the power series, for T20, I'm going to be looking at H divided by 2 squared, H divided by 4. So in the original series, every place where you see the letter H, Replace it with h over 4 and write the answer down. T20 is the true value plus 1/4 alpha 1h. When you square 1/4, you get 1/16. So that's where the 1 over 16 alpha 2h squared comes from. When you cube 4, you get 64. An observant person will notice that these two coefficients differ by a factor of 2, just as the other pair did. So calculate 2 to the 1 power times T20, which is 2 to the 1 power times the true value plus twice times a fourth is a half, twice times 1/16 is 1/8, twice 1 over 64 is 1 over 32, and we can write this expression out. Compare this with T10, which, as I said, we've previously calculated. You'll notice that the h to the first power terms match up now. So if you calculate 2 to the first power times T20 minus T10, if you do the subtraction, you end up with the true value minus 1/8 alpha 2h squared minus 3 over 32 alpha 3h cubed, and so on and so forth. So just as before, I have a combination of two things which used to contain an h to the first power, but now doesn't. This is going to be a quantity that estimates the true value to use fancy language, order h squared. Having done this once already, we know what we're going to do. We're going to write it in that same odd way. The bottom of the fraction is just 1. This quantity is q minus 1/8 alpha 2h squared minus 3/32 alpha 3h cubed plus higher order terms. We will call this number T21, and T21 obeys this equation, which is the same as that equation. By taking two combinations of different pairs of these values, we obtain two different approximations which are accurate to order h squared. Returning to our table, initially we had the approximation based on h over 2, and h over 4. So these might be trapezoid rule approximations to some integral, for instance. We know how to calculate T11 and T21 so that the error terms for these two quantities begins with h squared. We used to have an h to the first power term in the error, and now we don't. It doesn't take great imagination to guess what we're going to do next. We're going to combine these two pieces in some clever way to get rid of the h squared piece. Whatever we get after we do that, we'll call it T22, and that'll be accurate to order h cubed. If I had more rows, I would have more columns, and I could continue this calculation. So let's write down what T11 and T21 are. We have previously calculated these quantities, so we don't have to do it again. This time there's a difference, though. This quantity is different from that quantity, but it's not different by a factor of 2, it's different by a factor of 4. So doing 2 to the 1 power times T21 will not make these terms match up. That's not going to get the job done. Instead, I have to multiply by 4, which is 2 squared. If I figure out what 2 squared times T21 is, I get 2 squared times the true value. 4 times 1/8 is a half. 4 times 3 over 32 is 3/8, and so on and so forth. So now we'll calculate 2 squared times T21 minus T11. And now you should begin to see why I've been writing things in this very odd way. In one of the columns, the coefficient that I'm thinking about is just 1, so it seems silly. After you get past that column, though, it's no longer 1. So if you do the subtraction, 2 squared times T21 minus T11 is 2 squared minus 1 times the true value, minus the quadratic term in h cancels out, and I get something that starts off with h cubed instead. We'll call this quantity T22. T22 obeys T22 is the true value minus some quantity of order h cubed. This should be even more accurate than the things we were doing in the preceding column. Generally speaking, if I'm working on column number k in my table, to eliminate the term that I wish to get rid of, I'll have to multiply by 2 to the k power. So initially, the 2 to the 1 minus 1 looked very odd, but now we see where it comes from. So obviously, we're going to have an algorithm to carry this plan out. We're going to select a positive integer nt, which is short for number of rows in the table, roughly. Nt is going to be the biggest index in our table. We'll select an initial spacing, which I'm secretly thinking of as being delta x, and we'll have this loop to initialize column k equals 0 of our table. Do I equals 0 to nt, ti0 is the approximation based on h, then reduce h by cutting it in half and go around and do it again. In terms of the original spacing, you'll have the approximation based on that spacing, the approximation based on that spacing over 2, then the original spacing over 4, 8, 16, 32, and so on. So having initialized column 0, if we believe what we've been talking about, we'll implement our idea this way. Do k equals 1 to nt, do I equals k to nt. We will have the entry in our table, row I, column k, is 2 to the k power times the number immediately to the left, subtract away the number above the number immediately to the left, and divide by 2 raised to the k power minus 1. Finish the loop, finish the loop. The numbers down towards the bottom should be more accurate than the numbers up above. And as I go across the columns, I am knocking away one error term after another. So these numbers should be very accurate approximations to the actual value of Q. This technique is called Richardson's extrapolation. As a side comment, that's not how people usually write this, though. Take the numerator and split off one term of tik minus 1. You could combine this and get your 2 to the k times tik minus 1 back again. The reason that people do that is you can write it as this fraction plus that fraction. And of course, 2 to the k minus 1 divided by itself is 1. The way people usually write Richardson's extrapolation then is this way. If you'll think back to the method of bisection when we were talking about f of x equals 0, this is a desirable way to write things because the new quantity is going to be the old quantity plus an update. If the method is working at all, these numbers will be getting very small, and this tends, as you'll remember from bisection, to enhance the numerical stability of the method. So summarizing, we initialize column 0, and then after that, we go across the columns of our table in a similar way to the interpolating table. These quantities, the TIKs, should be getting increasingly better and better at approximating the true value that we're after. This technique is called Richardson's extrapolation. Finally, sometimes you get really lucky and the power series that differs between the approximation and the true value only has even powers of h in it. This will turn out to be true for one of our popular numerical integration techniques. If this is the case, you don't have to knock out the h to the first power term or the h cubed or the h to the fifth because they're not there to start with. Similar thinking to what we've done for Richardson's will reveal what changes we have to make in our algorithm, and it turns out to be practically nothing. This method that we'll get by doing this is called Romberg extrapolation. In such a case, which is not always true, but in such a case, you initialize column 0 exactly as you did before. You do the rest of the table exactly as you did before. The only change is, instead of subtracting 1 away from 2 to the k, you subtract 1 away from 4 to the k. Romberg, when it works, is an excellent approximation method. Of course, this whole discussion is very abstract looking. We haven't seen a single actual approximation to anything so far. So coming up very shortly, we'll look at an example of where you actually can do this Richardson's extrapolation and also the Romberg extrapolation. Until then, I hope everyone's having a good day. I'll talk to you again soon.